For Nuclear Science Week, I got a chance to spend a few days exploring Chalk River Laboratories, or known as CRL, one of several nuclear science and technology sites owned by Atomic Energy of Canada Limited and managed and operated by the Canadian Nuclear Laboratories, or CNL for short. Alongside my friend and travel buddy Mohamad Saleh, we went on a road trip to visit CRL. A short 5-hour drive from Toronto later, we arrived at a town 2 hours from Canada's capital city, Ottawa. Located on the traditional territory of the Algonquin and Anishinaabe peoples, Chalk River Labs is an extraordinarily massive campus with over 120 specialized lab facilities. It's where Canada's nuclear industry originated. Once considered a secret location for Canada's nuclear program, Chalk River Labs is home to several unique and historic nuclear reactors, like the now fully decommissioned Zero Energy Experimental Pile, ZEEP, the National Research Experimental, NRX, and the National Research Universal Reactor, and a little known gem which we got rare access to, an operating reactor on site called the Zero Energy Deuterium Reactor, Z2. Yeah, that's a pretty cool name. While these reactors may not look like a can-do, they all play a role in developing this technology that we rely on today. You see these can-do power reactors right here? They are all some of the only power reactors to produce both electricity as well as medical isotopes. And this simply would have remained a dream if it wasn't for the research that took place here at Chalk River Laboratories. Remember, this campus is a licensed nuclear site, and not many outside of the industry are given access to some of these areas. So filming here is also a rare privilege, which is why we had to be given special permission to film here. A lot of the footage that you see in this video has never been shown on a public channel like YouTube before. So this is a rare treat for both me and you. Alongside legacy reactor technologies, there is a lot of ongoing research and innovation coming from CRL, including from their high temperature fuel channel lab and their fuel fabrication labs. Yes, we got a chance to see TRISO fuel in person. We also learned about robotics, remote tool development, unique inspection tooling, how nuclear will support space exploration, and even we had the chance to walk through the location that may hold Canada's first nuclear waste disposal facility, the near surface disposal facility for low-level waste, or short for NSDF. We hiked up this proposed site. So this was an all-out adventure and experience of a lifetime. These few days, Mohamad and I, having backgrounds in nuclear engineering, felt like Charlie in Willy Wonka's chocolate factory. Hey friends, my name is Osama. I have a background in nuclear engineering, and on this channel, I help demystify nuclear technologies by simplifying them. I also help create educational resources like this video. Alright, so let's dive into the site itself. There's one word to describe Chalk River and the area surrounding it, and that word is magical. Driving up to the site, you immediately are hit by a combination of fresh, crisp air and the fragrance of pine trees that immediately fill up your lungs. It's a real treat just being in an area fully immersed in nature. In this area, animal life is vibrant, as you'll regularly come across deer, moose, wild turkeys, Canadian geese, and bears. There's a lot of work being done here to preserve, monitor, and protect the land. Getting to the Chalk River site itself, it's a massive campus situated on the Ottawa River. If you're lucky like us to come here during the fall season, you'll get a dose of those vibrant fall colors. As you look into the horizons at those rolling hills located in the neighboring province, Quebec. Alright, so our first stop on this visit is the NRU, or the National Research Universal Reactor. This is a legacy reactor technology deployed after its predecessor, the NRX. For decades, this multi-purpose facility was used to produce life-saving radioisotopes that treated over 1 billion people worldwide. It was a neutron source for Nobel Prize-winning research and a test bed for fuels and materials for future nuclear power reactors. When operating, this reactor generated enough radioisotopes to treat and diagnose over 20 million people across 80 different countries every single year that it operated. Yeah, that's incredible. Now, it was such a valuable resource to the world that in the year 2007, when the reactor was unexpectedly shut down for maintenance and upgrades, it resulted in a worldwide shortage of medical radioisotopes. Now, this prompted the Canadian House of Commons to pass an emergency legislation to authorize the prompt restart of the reactor. Since being shut down in 2018, research reactors across Australia, Europe, Russia, and South Africa have since met these demands.
Hey friends, we are at the NRU reactor, which is a really cool reactor that heard a lot of great insight on. Yeah, so we're going to be going into this reactor site and check it out. This is a model of the reactor. As you can see, this is one of Canada's most powerful research reactors, which was shut down a few years ago, but it's still here. Gonna go check it out. This is the reactor core. It's a cool little model of the reactor, but excited to show you all how it looks from the inside.
Taking us inside this legend was Dave Delano, former facility authority for the NRU, as well as Dan Simmerd, former senior reactor shift engineer. As soon as we enter the facility, we are met by the Canadian Neutron Beam Center, which is housed within the NRU. The CNBC used a variety of instruments connected directly to the reactor face and beam ports. It used neutrons from the NRU to probe deep within materials to solve industrial challenges. This equipment was used by both the industry and academia for important experiments.
So what you see behind here, the dual spec is one of our biggest spectrometers, neutron spectrometers. So these are connected to the reactor face, and behind this is a port that will allow neutrons to come out into the spectrometer.
All right, so this is the specific spectrometer which was used by the Nobel laureate Bertrand Brockhaus. Yeah, this is cool and kind of reminds me of the time we went to the McMaster nuclear reactor to check out where Bertrand Brockhaus also did some cool experiments. All right, so one of the highlights was going all the way to the top of this reactor and standing on the reactor face. When this reactor was operating, it was safe to walk on top. I know, that's pretty cool. Now, these little circles on top of the reactor face is where both fuel and isotope production rods would be inserted. So as the reactor operated, the target rods would be exposed to neutrons and later harvested for radioisotopes.
So while we were operating then, so that's the history, that's the design, we had three main missions. All right, so our first mission, which we're arguably most well known for, is our isotope production. All right, we produced a number of different isotopes, both for industrial and commercial uses. Notably, we produced a lot of the world's supply of molybdenum-99. So molybdenum-99 decays to technetium, and it's technetium that's used in a number of medical imaging and treatments. So it was a very common treatment. So before 2009, if you knew people in Canada, arguably North America, that had gone through radiotherapy, nuclear therapy, there's a very good possibility that material originated here.
What amazed me most was the condition of this facility. It's as if it was operating right now. Someone walked in here, they wouldn't be able to guess this place started operating 66 years ago. After checking out how this reactor was fueled, as well as appreciating the sheer magnitude of his contributions to the world, we were off to check out the reactor control room. This is where the magic happens. Before leaving the reactor area, we scanned our hands and feet for any traces of radiation. Although this place is routinely cleaned and monitored, regularly scanning areas of your body are standard precautionary practices in the industry. Yeah, if you go to any other site in Canada, you'll be going through the same process.
We are in the control room now, which operated this reactor at one point. And as you can see, there's some really cool dials and buttons in the background. And let's check it out.
This control room is where the magic happens. This is where senior reactor shift engineers would stand when reactor shutdown and startup would take place. These dials, lights, and switches are used to both monitor and control reactor activities. Walking into this control room was like traveling to a moment when this reactor was alive. Seeing the buttons, switches, gauges, panels, all analog technologies, by the way, that was designed to control this beast. Now, NRU was the first reactor in the world to execute on-power refueling. Yeah, on-power refueling is when reactors are operating and you can refuel them at the same time. It's a defining feature of the CANDU reactor. It was a work of art. Going into this control room, I could imagine these panels just lighting up as if it was once operating right now. And a team of reactor operators monitor it at all times. Just how many systems are connected to these panels? How many years did it take for operators to get get trained to operate this beast? As I stared at those panels, so many questions went through my mind. Fun fact, this control room had to be occupied by at least 2 operators at a time, and there was continuous presence in that room for over 61 years. Before leaving the facility, we did one last body scan and monitoring before we head off to our next location. It wasn't a surprise that we came out clean. Alright, next we hiked up a site which may soon be home to Canada's first low-level waste disposal facility, or NSDF for short. Yes, this site recently received approval from the Canadian Nuclear Safety Commission, and it will be, like I said, Canada's first low-level waste disposal facility. Project Director Steve and environmental engineer Craig gave us an extensive tour of the site, which will house this first-of-a-kind facility in Canada. It was a chilly morning with fresh air and fall colors all around us. It felt nice to explore this area. This area was uniquely chosen based on the bedrock composition, the flow of water, as well as several other factors. Extensive environmental studies have taken place at this site to ensure that a facility in this area will keep wildlife and the ecosystem safe. Project Director Steve gives us a deep dive into more details around this proposed site and facility.
Ottawa Valley and on the site for the near surface disposal facility. A couple interesting points for this facility. Obviously, we're in a forested area right now. This area was chosen because it's situated on a bedrock ridge. Water flow is actually away from the Ottawa River, so there's quite a long transition time for groundwater or anything that falls within the site to make its way through the Perch watershed and into the Ottawa River. It's obviously, when it's constructed and completed, it's home for about 1 million meters cubed of low-level radioactive waste.
On January 9, 2024, the CNSC, or the Canadian Nuclear Safety Commission, officially approved the construction of this disposal facility, acknowledging that the NSDF project is robust, supported by a strong safety case, able to meet its required design life, and sufficient to withstand severe weather events, seismic activity, and the effects of climate change. The Commission found that the site selection and NSDF design are in alignment with the International Atomic Energy Agency standards.
Some interesting sort of construction items for this facility is that we're actually going to be doing a mass excavation to bedrock of the entire engineered containment mound, which is really this area behind me. We remove about 600,000 meters cubed of overburden. We're actually blasting into the bedrock to have a complete stable base for the facility. There's another 200,000 meters cubed of bedrock removal, and then we're bringing in aggregates, all engineered aggregates, to construct the engineered containment mound, the berm, and the liner system, which is going to ensure that the water is collected within the ECM and then pumped and treated through the water treatment plant.
Well, the real question is, how safe is this facility, especially for wildlife and the environment in the area? To answer this question, we've got Craig, who has a background in environmental engineering, to tell us a bit more about this place.
Perfect. So I guess the engineered containment mound, or the NSDF, in terms of safety. So everything we do in safety in nuclear, we always do redundant, the Swiss cheese effect. You have all your safety barriers, and for an incident to occur, you have to have all of those holes line up. So redundancy is the key. You have a safety feature on top of a safety feature so that there is no release off to the environment, no release to the public. For NSDF, that starts with location. So as Steve mentioned, the siting location, we picked Chalk River. We started with 15 sites across the Chalk River site, and this area was selected because of that bedrock ridge and the topography. Water that does hit this facility, be it non-contact water, which is just traditional storm water, and contact water, which is anything that could hit waste or potentially could hit waste, travels in that direction away from the river. So right off the bat, you kind of have your location selected for safety. The containment mound itself, the way we do that, traditional landfills, traditional waste management facilities will have a single liner. We put a dual liner in. So a dual liner, the first one would be a clay base. You have a leachate detection layer, which is if something did happen to leak through the liner, we have alarms, points to tell us that something's occurred. And then on top of that, a leachate collection layer. So those two barriers will trap leachate that percolates through the waste and send it off to wastewater treatment plant for treatment, rather than it seeping through the liner or ponding on the liner, causing those leaks. So we kind of have that dual system built into the liner. And then on top of that, once you're in a containment mound, once the whole thing is full, we put a cover over the top. The cover is designed to shed off precipitation, so it's impervious. So you don't have, after the containment mound is closed, you don't have more water contacting the waste, more leachate generated. That top cover also has features in like a rock barrier, which stops tree roots from infiltrating the waste or animals burrowing into it. With that cover, with that base, the waste is contained and then contained again by the siding, by the bedrock ridge, until it's decayed off, till it's no more hazardous than a traditional landfill.
Craig's description of the safety systems were simple, choosing multiple systems which all work together to ensure that the environment and wildlife is not exposed to any harmful waste or radioactive byproducts. I really enjoyed learning about the science behind what makes this facility so robust.
You know, some of the material we presented in our regulatory hearings, and some of the experts that we've engaged to review the design that's been done, including experts from Queen's University who did comparisons to a variety of facilities, a number in the US, and have certainly concluded that the advancements made in the NSDF far outweigh any of those facilities. So we've taken a lot of existing practices in place, then built in additional redundancy and features to improve it.
Steve also spoke to the study of international concepts. Standing here with the breeze blowing by and seeing all of the wildlife and nature surrounding us, it made me appreciate the extensive research, design considerations, and international benchmarking it takes to put together construction projects like these. Design approaches that ensure that both nature and wildlife alike are protected for generations to come are ethical in their very nature. Canada's adherence to strict regulatory standards, as well as professional excellence by experts like Steve and Craig, should give the general public confidence our industry and disposal sites are like this. The High Temperature Fuel Channel Lab is a unique world-class facility where research and testing at high temperatures and pressure takes place.
About 30 years history. They originally was located in Whiteshell. It's named the High Temperature Fuel Channel Lab because it was originally meant to do testing on fuel channel. Now that's here, still it keeps the name, but we also do other types of experiments. I'm in a section called the High Temperature, High Pressure Experiment section, and we do, well, as the name implies, experiments on high temperature and high pressure.
Experiments at high temperatures are required to demonstrate that nuclear power plants continue to operate safely and are cooled at all times. Remember, it's one of the golden rules of reactor safety: cool. Now, nuclear fuel runs at a temperature over 1,100 Celsius. Yes, that's degrees Celsius and equivalent to around 2,000 degrees Fahrenheit. That's hot. Labs like this one are used to conduct experiments on new nuclear technologies and concepts, from new instrumentation to monitor reactor performance to new cooling methodologies. The behavioral materials used in current reactors at postulated high temperature scenarios is tested as well. In addition to CANDU reactor fleets, extensive testing and research is being done for small modular reactor types which deploy various cooling concepts like using heat pipes for passive heat removal. Labs like this one are used to conduct experiments relevant to the existing CANDU reactor fleet. Behavioral materials and coolants used in the reactor are tested over a broad range of conditions. The materials range from the sheet that covers the fuel, which is around a couple of centimeters diameter, to structures within the reactor vault, which is tens of meters. It was fascinating to see a variety of instruments used to conduct this research at postulated reactor conditions. It's not every day that you come across a lab which can simulate high temperature conditions comfortably, mimicking conditions you would find in an operating nuclear power reactor. In light of nuclear safety, it just goes to show the level of exceptionalism. To give the public some reassurance that reactors that provide clean energy to power our homes and businesses aren't experimental reactors. There is an extensive amount of testing that takes place before any of these designs are deployed or even prototyped. From materials used to contain nuclear fuel that is cooled from high operating temperatures to the ridges, bends, and most subtle design features integrated within cooling circuits operating at lower temperatures than the fuel, but still at hundreds of degrees Celsius.
So this bundle here actually is like supposed to be the 100,000th CANDU bundle. So this used to be in the Prime Minister's office, and eventually they, didn't want it to be in the Prime Minister's office, and it came back to us. This is not a real fuel, it's just dummy fuel element.
Right, so next we are off to the Fuel Fabrication Lab. Researchers gave us an overview of the research going on at CRL in the area of fuel, as well as one aspect which is the next generation of fuels called TRISO. This is my first time seeing a surrogate TRISO particle up this close. Surrogate refers to the fact that the core of the TRISO particle is made up of a surrogate non-nuclear material, such as zirconium oxide, opposed to uranium dioxide or uranium oxycarbide, which would be used for a fueled TRISO particle.
And then is the goal at the end, let's say these want to be used in the CANDU reactors for say, right? Would that be shaped into how that goes into bundles?
It would have to, yeah. It would go into, so if it were to be incorporated into CANDU, then you take how many millions of these integrated with a matrix. No, traditionally it's a graphite matrix, and then it's incorporated into this shape.
All right, for those that don't know, TRISO or tristructural isotropic is advanced and accident-tolerant nuclear fuel that is comprised of either uranium dioxide or uranium oxycarbide kernel, which is approximately 0.5 millimeters in diameter. This is surrounded by alternating layers of graphite and silicon carbide, so the total outer diameter accounts for around 1 millimeter. Now, the multi-layered design serves as a containment system for fission products that are produced during the fuel's lifetime in a reactor and provides improved structural resistance to neutron irradiation, corrosion, oxidation, and high temperatures when compared to traditional reactor fuels.
Hi, I'm Regan Osmond. I'm a fuel research scientist at CNL, and this right here is a X-ray computed tomography machine. So I use it to non-destructively look inside of small objects, pieces of reactors, different fuel components. And yeah, I can show some examples. So now I'm just seeing a slight, like this is all the whole object right here.
This is essentially what we're trying to build. Now this one is open, so if this actually leaked out onto our instrument, it would probably cause damage to the measurement head. So we're going to go from this encapsulation technique to also go into more of a nickel welded capsule, which we got one right here we're going to try and use. So just put the salt in there and then weld the
Next, we got a chance to tour the Mechanical Equipment Development Lab where we met Scott Reed, who is an R&D researcher.
Well, thank you very much, Osama, and really appreciate you coming by our lab to talk about what we do here. So as I mentioned, I'm a mechanical engineer for the Mechanical Equipment Development branch. We're a branch that primarily develops first-of-a-kind tooling for the nuclear industry.
The mechanical equipment development team uses their lab's manipulator mockup to test out the different tooling and equipment they design and build for projects going on within Chalk River Laboratories and beyond. Here, he demonstrates how standard manipulators work, how they can be used to handle highly radioactive materials and isotopes.
So these are mechanical manipulators. They essentially just follow the path of what I'm drawing here. And they're a 2-finger manipulator, so I can squeeze the gripper here, I can lock it out, and generally move it around. We also have, these are motor operated, so we can extend the reach if we need to. But generally everything here is mechanically connected. So it's mechanically connected through ribbon tape, and this allows for a very robust design, very radiation tolerant, and quite useful. I mean, we've had manipulators like this on our site for well over 50 years in operation, and these hot cells are working day in, day out. So
this brings me back to the time where we saw the hot cell facility, as well as had the chance to use manipulator arms at the McMaster Research Reactor.
There's a number of projects in the branch right now that are all working in support of the reactor fleet in Ontario and abroad. So we've got some research projects here that are working with Z2 to design custom equipment to do some novel fuel experiments in the Z2 reactor. We're also working with places like Gentilly 1 and Douglas Point to produce tooling to go in and do characterization work there in support of their decommissioning operations. We're also involved with current fleet operations, so places like OPG and Bruce Power who come to us to assist in the development and operation of tooling that goes into, say, the fuel channels to perform fuel channel maintenance.
Nuclear power reactors are the ideal power source for outer space because they're energy dense and they aren't dependent on the weather. The most powerful potential applications for these reactors are to produce power in space stations for years and years. No other energy source can do that. Hence why I was lucky enough to have a conversation with research scientist Justin Spencer, who is leading world-class research on nuclear fission reactors in outer space.
A lot of that ultimately comes down to what's referred to in the space world as ISRU, in situ resource utilization. Ultimately, a major use of the electricity and heat, as you're mentioning, for this would be ISRU. That likely is going to follow a while after the establishment of a place for people to sleep. Their first job will be getting a place set up, habitable, and then start scaling up. And actually, when they move on to more significant ISRU, which will in particular include the extraction of water from areas of the moon or Mars where there is some water in the soil, some small ice caps in Mars, and that's.
We talk about the unique complexities that make outer space a unique environment for reactors. What is the goal? How will environmental conditions in space impact the design? What types of fuels, coolants, and materials are used to build these reactors? For those working in the nuclear energy industry, the idea of space reactors is very novel. You never hear about it. However, with companies like SpaceX making space travel more economical, it makes sense why Canadian Nuclear Labs is on the forefront of this research. Shout out to AECL's Federal Nuclear Science and Technology Work Plan, FNST. It's a unique program which gives government agencies like the Canadian Space Agency access to the people and labs here at CRL.
So extraction of water, also cracking it into oxygen and hydrogen so you can produce your own fuel, which is a lot better than having to ship it up from Earth. But when they move to those sorts of things, they'll be looking for much larger power sources. So at that point, the idea is kind of that we'll walk before we run. Let's build a small reactor that produces a modest amount of electricity, maybe some process heat as well, as you're mentioning. But I think the secondary systems that would be required for piping that heat around for various purposes are likely not where we want to start with this. We probably want to focus on a self-contained unit and then use the electricity for the process heat initially. But after we've done that, then we can start to dream bigger and scale up the reactor, higher power, maybe higher temperatures, and maybe the use of process heat rather than just dumping it all to space with our radiators.
If you'd like to check out this full conversation, I do encourage you to head out to my podcast channel called Going Nuclear, where I speak with technical and communication experts and thought leaders in the nuclear industry. You'll see an episode featuring this subject. CRL Science Collaboration Center is a special place. The center has a clear mandate to bring together scientists and experts across this nuclear campus. And as you can tell, this building has all the bells and whistles. The moment you walk inside, you inhale a fresh fragrance of spruce. When spending enough time here, you do feel that the architecture and design of the building is true to the local nature that surrounds this site. These are the very first federal buildings constructed using mass timber, a more sustainable, carbon-friendly building product. The views from the top of this building are surreal. Getting a breathtaking view of the Ottawa River, as well as rolling hills with fall colors, is simply mesmerizing. Now imagine getting together with colleagues here to collaborate on projects, research, and other groundbreaking technology. The theater hall is another highlight, which is used to host movies, workshops, and conduct town halls. The collaborative spaces throughout this building really do make it a special place. All right, so now for a reactor you've all been waiting for, the Nuclear Power Demonstration Reactor. This reactor helped propel Canada to the international stage to become a handful of nuclear nations to master the craft of controlling nuclear fission and creating electricity, the lifeblood of modern-day civilizations. This was a demonstration reactor that was used to test new fuels and materials, as well as train an entire generation of nuclear operators who would go on to operate advanced reactor units across Canada, like Bruce, Pickering, and Darlington sites. The NPD was also used to train professionals internationally from where AECL was selling its nuclear reactors, notably Pakistan and India. Because of the operational excellence of this legend, there are more than 70,000 nuclear professionals that are employed right now across Canada in the nuclear industry. It's Canada's first power reactor, and it's a special place. Mohamad and I had the chance to walk into the heart of this facility. Now, leading this tour was Mike English and Katie Shorter, who took us to the heart of this facility. Seeing the first generation components that would iterate into the modern day CANDU was enlightening. It brought us back in time to when this facility once operated. Many of the components that enabled this reactor to operate for decades were still intact, known as the safe storage with surveillance state. This truly was a rare opportunity, going inside a site that has been closed off for several years and traveling back in time to a moment where Canada was racing to innovate and lead the frontiers in nuclear innovation. They say history repeats itself, and I learned what that meant here. The energy we felt here is the same renewal we are feeling right now in the Canadian nuclear industry. Canadian Nuclear Laboratories is indeed part of that revitalization. The world-class research and expertise are so important. Although many areas are already decommissioned, this was just a phenomenal site to visit. When I came to the site, I thought the last operating nuclear reactor at this facility was going to be the NRU, shut down in 2018. But to my surprise, there is still an operating reactor at the site. It's called the Z2, or the Zero Energy Deuterium reactor. Coming online in the year 1960, it's still operating today in mint condition. No moving parts, no radiation hazards. It's a sweet little reactor. This is a low power reactor which is used to perform reactor physics measurements and conduct fuel studies. It's also still regularly used by the industry to calibrate equipment that goes into nuclear power reactors, like measurement devices such as neutron detectors used to measure how nuclear power is being produced in the core of nuclear power reactors. The Z2 is also used to calibrate ionization chambers, as well as self-powered flux detectors, which are used throughout a CANDU reactor core to measure neutron flux, and which are tied into reactor monitoring and control system. This is such a valuable resource to the industry. This reactor was used to confirm reactor physics designs of all of Canada's power reactors, which includes the next generation designs, which haven't even been commercialized yet. Fun fact, the Z2 reactor core has been rearranged over 2,500 times, which is a testament to its flexibility. Here's a picture of us going inside the concrete shielding, which gives us access to outside of the large aluminum tank that holds the core, which is surrounded by a graphite reflector. Low power means all areas of the reactor are very accessible, including being able to enter the reactor vessel itself. It's kind of a neat feature. We also got the chance to stand right on the deck plate above the reactor core itself. The tank and fuel assemblies that hang inside the reactor were phenomenal. Here's the last picture of us going inside the control room. These pictures are a rare treat and a memorable experience. It felt incredible to just stand here and acknowledge the importance of a facility like this. Well, there you have it. That was the journey to Atomic Energy of Canada's Chalk River site, operated and managed by Canadian Nuclear Laboratories. Check out some of my other videos where I tour facilities across the world, and to join us on our next adventure. Till then, take care. Bye.